somewhere, in one of the coldest, darkest corners of our solar system, a small moon is doing something it has no obvious reason to do. It is spraying material into space, not as some ancient scar from a long-dead collision, but continuously, right now, in this very moment, for as long as anyone has been watching. For 2 decades, scientists have asked the same question from a dozen different angles, and every answer has pointed the same quiet way. Something beneath that ice is warm. Something beneath that ice is moving. And whatever is riding that spray out into the vacuum of space may be carrying the answer to a question humanity has asked for centuries. What is actually down there, and why can no one look away from it? If this kind of quiet drift through the solar system is something you look forward to, a like and a subscribe helps this small channel keep going. Let your shoulders drop and get comfortable. In 3, 2, 1, liftoff. Far beyond the orbit of Mars, past the asteroid belt, out where sunlight arrives so thin and pale it can barely be called daylight, the great ringed planet Saturn moves through the darkness on its own slow circuit of the Sun, a journey so long it takes nearly 30 years to complete just one. Around it, in a family of dozens of moons of every size and character, drifts one small, quiet world that most people have never heard of. It circles Saturn in just over a day, a quick little loop compared to the giant it orbits. One modest member of a family that, by the time anyone thought to send a spacecraft there, was already known to include several dozen moons of every size, from tiny, irregular, captured rocks only a few miles across up to Titan, a moon larger than the planet Mercury itself. Set against neighbors that large and that varied, there is nothing about this particular moon that would catch your eye. It is small, it is quiet. It is, by nearly every measure astronomers use, one of the least remarkable bodies in the outer solar system. Its name is Enceladus. It was first seen by the German-born astronomer William Herschel on the night of August the 28th, 1789, through a telescope 40 feet long that he had built with his sister and lifelong collaborator, Caroline, who was no mere assistant in that partnership. Caroline Herschel would go on to discover several comets of her own and become, a few years later, the first woman in England ever paid a salary for scientific work, a small pension granted for her role in keeping her brother's enormous telescope running. William Herschel was already one of the most celebrated scientists alive, having discovered the planet Uranus 8 years earlier, and that night he was doing exactly what had made him famous in the first place, patiently sweeping his telescope across Saturn and its 5 already known moons in search of anything smaller instruments had missed. Even with the largest telescope on Earth trained on the ringed planet, Enceladus appeared to him as little more than a faint pinprick of light, a 6th moon added to the family. His son later named it, along with a 7th moon found weeks afterward, for a family of giants out of Greek mythology. For the better part of 2 centuries afterward, that was very nearly the entire sum of human knowledge about Enceladus. A name, a rough orbit, and one small, curious detail nobody could explain. It reflected almost all of the sunlight that touched it, more than nearly any other object ever measured in the solar system, brighter even than fresh snow on a clear morning. Most worlds darken with age, coated in dust and scarred by radiation. A surface that stays this bright usually means something keeps renewing it, and for a century and a half, nobody had the faintest idea what that something might be. The first real opportunity to look closer came in 1981, when the Voyager 2 spacecraft swept through the Saturn system on its long grand tour of the outer planets, a single quick pass, never intended to linger, on its way toward two more distant worlds, still waiting to be visited. Voyager 2's cameras, hampered by a scan platform problem during the encounter, never managed a clean look at Enceladus, and the distant images it did capture were strange enough to be remembered for decades afterward. Parts of the surface were pockmarked with craters, exactly what 4.5 billion years of impacts should produce. Other parts were almost entirely smooth, pale, and young-looking, as though something had wiped the terrain clean and started over comparatively recently. On a body this small, this cold, and this far from the sun, that should not have been possible. Small, icy worlds are supposed to freeze solid within their first few 100 million years and stay that way. Voyager 2, with a packed itinerary and two more giant planets still ahead of it, left the question sitting there unanswered and moved on, and there the matter rested for another generation. It would take a very different kind of mission to pick that question back up. The Cassini spacecraft, a joint undertaking of NASA, the European Space Agency, and the Italian Space Agency, launched from Cape Canaveral in October of 1997 and spent nearly 7 years crossing the solar system, looping past Venus twice, and then Earth and Jupiter in turn to borrow a little speed from each, before finally settling into orbit around Saturn in the summer of 2004, the first spacecraft in history to do so. Leading the team responsible for its cameras was a planetary scientist named Carolyn Porco, who had spent years studying the rings and moons of the outer planets, and who now, for the first time, had the chance to look at this small, oddly bright, oddly young-looking little moon more closely and more patiently than anyone in history ever had. Unlike Voyager 2's single hurried pass 2 decades earlier, Cassini was built to stay in the Saturn system for years, circling and recircling, free to return to any one moon again and again if something there seemed worth a second look, carrying with it a dozen scientific instruments built by teams scattered across the world, each one designed to study a different piece of the Saturn system. Titan had always been the mission's marquee destination, the reason the Huygens probe had been carried along in the first place, and on January the 14th of that same year, just weeks before the first Enceladus flyby, Huygens had already made history, descending safely through Titan's thick, orange atmosphere and touching down on its surface, the first landing ever accomplished on a moon anywhere in the outer solar system. By any reasonable measure, the mission had already succeeded before that year was even a month old. Nobody involved expected a small, second-tier target, barely mentioned in most of the mission's early planning documents, to end up rivaling that achievement for attention within the very same year. At first, there seemed to be little reason to expect anything remarkable from this small, quiet neighbor. Enceladus remained, on paper, a minor stop on a mission built around its far larger companions, worth a handful of flybys and not much more. Every planet or moon with enough internal activity to generate a magnetic field of its own, the way Earth does deep within its molten iron core, projects an invisible shield out into the space around it, one that shapes and redirects the charged particles streaming outward from the Sun. Saturn, being far larger than Earth, carries a magnetic field of its own too, vastly more powerful, stretching for millions of miles in every direction and sweeping past every one of its moons in turn. Most of those moons, small, cold, and utterly inert, simply sit inside that enormous field without disturbing it in any noticeable way, much the way a small stone lying at the bottom of a slow-moving river barely changes the current passing over it. But early in 2005, as Cassini began a planned series of close passes by the little moon, that quiet reputation started to crack. On the very first of those flybys, in February, an instrument called a magnetometer, built to measure the strength and shape of magnetic fields, returned a reading that made almost no sense at first glance. Saturn's magnetic field lines should have swept past Enceladus more or less undisturbed. Instead, the field appeared to bend and drape itself around the little moon, gently but unmistakably, the way it does around a much larger body that carries its own thin envelope of gas. Charged particles surrounding the world, dragging a passing field out of shape as it moves through them. Enceladus was not supposed to have anything like that. It was far too small and far too cold to hold onto a meaningful atmosphere for any length of time. Whatever gas escaped from it should have drifted off into the vacuum of space almost immediately, with nothing left behind to bend a passing magnetic field at all. Mikhail Doherty, the scientist in charge of that magnetometer, offered an explanation that struck some of her colleagues as almost far-fetched at the time. Perhaps Enceladus was not holding on to an atmosphere in any permanent sense. Perhaps it was making one, continuously, venting a thin trickle of gas into space fast enough to keep a faint cloud hanging around it at all times, too faint for any instrument to have caught it until now. A second flyby in March returned more of the same kind of puzzling, inconclusive evidence, enough to convince the mission's scientists that something genuinely unusual was happening near Enceladus's south pole, but not enough, on its own, to say exactly what. Every flyby of a moon this small has to be planned with tremendous care, long before the spacecraft ever arrives. Its trajectory worked out months in advance by navigators calculating exact angles and velocities down to fractions of a degree, because a spacecraft moving at many thousands of miles an hour has almost no room for error when passing within a few hundred miles of solid ground. That left the third and closest flyby of the year, scheduled for July, carrying an unusual amount of anticipation among the teams who had spent months preparing for it. On July the 14th, Cassini made its nearest approach yet, a careful, deliberately risky pass that brought the spacecraft within roughly 109 miles of the surface, close enough to resolve details no human eye had ever seen, and close enough that a navigational mistake could have ended the encounter and possibly the spacecraft in an instant. The gamble paid off, and that 109-mile pass would not stand as a record for long. In the years that followed, as Cassini kept returning, mission planners found the confidence to fly closer still, eventually threading the spacecraft through gaps of only a few dozen miles above the icy surface, and on at least one occasion, directly through the heart of the plume itself, close enough to sample, in a very literal sense, whatever the moon was actually made of. Each of those closer passes carried its own risks, approved only after the previous flyby's data had been carefully reviewed and the trajectory adjusted all over again. But each one also brought back more information than the last, slowly assembling a portrait of Enceladus far more detailed than the cautious, single-glancing pass of Voyager 2 could ever have produced. Within days of that first close pass in July, several of the spacecraft's instruments had returned strikingly consistent answers, each one arriving at the same extraordinary conclusion by an entirely different route. An ultraviolet spectrograph aboard the spacecraft, overseen by scientist Candace Hansen, was pointed at a distant, faraway star just as Enceladus passed directly between that star and the spacecraft. Normally, when a solid moon passes in front of a star, the starlight simply vanishes, cleanly and instantly, blocked by an opaque surface with a sharp, well-defined edge. This time, it did not. The star's light dimmed gradually, flickered, and grew faint in stages rather than vanishing all at once. Precisely the kind of signature you would expect. if the light were passing not through empty space or past a solid edge, but through a diffuse, hazy cloud of gas and scattered ice particles hanging just above the moon's south pole. At almost the same time, on the other side of the mission, Carolyn Porco's imaging team was working through photographs taken during that same flyby under a very particular lighting arrangement, with the sun positioned behind Enceladus so that anything hovering above the surface would be lit from behind, the way ordinary household dust becomes suddenly visible, catching the light when it drifts through a narrow beam of afternoon sun crossing a quiet room. And there it was, plain and unmistakable in the raw images once they came down, tall, faint plumes of icy material rising from the south polar region and arcing outward into the darkness. Several distinct jets, braided together into a single towering feather of fine ice crystals, catching what little sunlight reached that part of the solar system and scattering it back toward the camera. In that very first set of pictures, the team could make out only a handful of individual streams, merging together into the one broad plume everyone would soon be talking about. It would take years of additional, closer flybys and increasingly careful processing of the images before the fuller picture finally came into focus. Not just a handful of vents, but something closer to 100 separate jets scattered along the four fractures, some no wider than a garden hose, others considerably larger, each one apparently able to strengthen, weaken, or shut off entirely on its own, more or less independent of its neighbors. But even that first glimpse, on that first afternoon in July of 2005, was more than enough. This was not some frozen relic of ancient activity, a scar left behind by a long-dead process and preserved unchanged for billions of years. It was happening in that very moment, actively, while the spacecraft watched, material visibly leaving the moon and continuing to leave it for as long as anyone kept the camera pointed in that direction. Before any of it was shared beyond the mission's own science teams, the data was checked, and checked again, run past instrument specialists who spent days ruling out camera glare, cosmic ray hits, and every other mundane explanation that long experience had taught them to suspect first. Discoveries this strange do not get announced on a first look. They get interrogated until nothing simpler is left standing. It is difficult, from this distance in time, to fully convey how strange this was to the people looking at it that summer. At that point, only two other solid bodies anywhere in the solar system were known to have any kind of ongoing eruptive activity at all: Jupiter's moon Io and Neptune's moon Triton. And in a small coincidence of timing, both of those earlier discoveries traced straight back to the very same Voyager program that had first glimpsed Enceladus's puzzling terrain. Voyager 1 had caught Io's volcanoes erupting in real time during its own Jupiter flyby in 1979. Watching a plume rise more than 100 miles above the surface in a photograph, nobody had expected to find anything of the kind in. Voyager 2 had done much the same for Triton a decade later, in August of 1989, capturing dark geyser plumes streaked across its frozen nitrogen surface, landing almost exactly 200 years, to the very month, after Herschel had first spotted Enceladus through his own telescope. Both of those worlds had a clear, well-understood reason for their restlessness. Io is squeezed and kneaded continuously by the ferocious tidal pull of Jupiter, the largest planet in the solar system, a gravitational vice so powerful that it keeps the little moon's interior partially molten, feeding a landscape mottled with sulfur and scarred by dozens of active volcanoes that never fully quiet down. Triton, sitting far out near Neptune, receives no such tidal squeeze, but it does receive enough of the sun's faint, distant warmth, along with a slow seasonal thaw as its polar ice caps shift across the decades to occasionally drive thin geysers of nitrogen frost a few miles into its own dark sky. Enceladus had neither of those advantages available to it. It orbits Saturn in a comparatively gentle, well-behaved path, without the kind of extreme, punishing tidal stress that keeps Io's interior molten, and it sits nearly 1 billion miles from the Sun, considerably farther out and considerably colder than Triton, with nowhere close to enough sunlight reaching it to explain an ongoing eruption of any kind. Saturn's own family of moons offered plenty of contrast to underline just how unusual this was. Mimas, one of Enceladus's nearest neighbors, wears a single impact crater so enormous it covers nearly a third of the little moon's diameter, a scar that has simply sat there, undisturbed, for billions of years. Tethys, a little larger than Enceladus, carries a crater nearly as large, along with a vast canyon system stretching most of the way around its circumference, all of it ancient, all of it long since finished forming. Dione and Rhea, bigger still, are covered nearly pole to pole in overlapping craters of every size, a visible record of billions of years spent quietly absorbing impacts and changing very little in return. Even distant Iapetus, one of the strangest moons in the solar system, strikingly bright on one side and nearly coal black on the other, has worn that same divided face for as long as anyone has been able to study it closely. Against that backdrop, an entire family of moons that had each, in its own way, settled into a long, quiet, geologically finished old age. Enceladus stood out as the one relative that had somehow refused to grow old at all, by the standards that had explained every other active world found up to that point, and by the standards set by every one of its own quiet neighbors. Enceladus simply should not have been capable of what the cameras and instruments had just shown it doing. Standing on that icy surface, had anyone ever been able to, the view would have been unlike anything available anywhere on Earth. Saturn itself would fill a huge portion of the black sky, its rings tilted wide or nearly edge-on, depending on the season, far larger and far closer than our own moon ever appears from the ground back home. The terrain underfoot would be smoother and colder than almost anywhere our own planet has to offer. Hardened, wind-scoured ice under a sky with no wind at all left to scour it, since Enceladus holds onto no real atmosphere of its own. And near the South Pole, rising silently out of those 4 long fractures, a faint curtain of fine ice crystals would climb slowly into the blackness overhead, catching starlight, catching the pale glow of Saturn itself, before drifting outward and away toward the rest of the solar system, carrying with it whatever secret still waited at that point to be discovered. The source of the plumes turned out to be that same set of 4 long, roughly parallel fractures cutting across Enceladus's south polar terrain, running side by side like claw marks raked across the pale ice, spaced with an almost unsettling regularity around the pole. The scientists studying them soon began calling them, informally, the Tiger Stripes, a nickname that stuck so firmly it eventually became more famous than the formal names the fractures were later given, names borrowed, a little improbably, from cities of the ancient world. One became Alexandria, one Cairo, one Baghdad, and one Damascus, continuing a long tradition observed throughout Enceladus's mapped terrain, of naming its craters and fractures after places and characters drawn from the tales of the Arabian Nights, a small, quiet touch of poetry applied to a landscape that had otherwise gone unnamed for 2 centuries. Each fracture ran for roughly 80 miles, a deep gash carved directly into the ice, and when Cassini's infrared instrument, called the Composite Infrared Spectrometer, essentially a highly sensitive thermal camera built to measure heat rather than visible light, turned its attention toward them, it found something just as strange as the plumes rising above them. The tiger stripes were measurably, unmistakably warmer than the frozen terrain surrounding them on every side, warm enough that the instrument could pick out the temperature difference from many hundreds of thousands of miles away, long before Cassini had even arrived close enough to photograph the fractures in any detail. Altogether, the 4 cracks were radiating something on the order of 3 to 7 gigawatts of heat continuously out into space, an amount of energy comparable to the combined output of a small city's worth of power plants, pouring steadily out of narrow cracks in the ice of a moon that, by every conventional model of how small, cold worlds are supposed to age, should have gone dark and silent billions of years earlier. Even at their very warmest points, the tiger stripes only reached temperatures somewhere in the neighborhood of nearly 200 degrees Fahrenheit below zero, a cold that would be lethal to an unprotected human being within moments, and that no laboratory on Earth has to work particularly hard to reproduce. But set against the surrounding ice, which sat hundreds of degrees colder still, that same brutal reading looked, by comparison, almost like a furnace glowing quietly in the dark. None of this fit the story astronomers had spent decades telling themselves about how small moons are supposed to behave. The underlying physics is not especially complicated, and it had been well understood for a very long time before Enceladus came along to complicate it. A body's ability to hold onto its own internal heat depends heavily on the relationship between its volume, where heat is generated and stored, and its surface area, where that heat inevitably leaks away into the surrounding cold. Large planets, with an enormous volume relative to their surface area, lose heat slowly, over billions of years. In much the same way, a large pot of soup left out on a kitchen counter stays warm long after a small cup poured from that same pot has already gone cold. Small bodies work the opposite way. They carry a great deal of surface area relative to their volume, and whatever heat they are born with, left over from the violent process of their own formation, or produced afterward by the slow decay of certain elements buried within their rock, tends to escape quickly on a geological time scale. By most standard calculations, a body Enceladus's size should have radiated away the last of its original formation heat within its first 200 or 300 million years, a process largely finished while the solar system itself was still less than 1/10 of its current age. Enceladus is small, even by the modest standards of moons, a little world with a diameter of roughly 313 miles, close enough to the length of the state of Arizona, measured from its northern border to its southern one, that you could lay the entire moon across the state and have very little room left over on either end. A body that size, sitting nearly 1 billion miles from the warmth of the sun and orbiting a planet whose gravitational grip is nowhere near as punishing as Jupiter's grip on Io, had no reasonable business retaining any usable internal heat by now, let alone enough of it to keep 4 separate fractures, erupting continuously into open space, visible to a passing spacecraft on its very first close look. And yet there it was, caught on camera, confirmed independently by 3 separate instruments built by 3 separate teams, all converging on the same impossible conclusion within days of one another. Word of the discovery spread quickly through the scientific community that summer, carried in hurried phone calls and hastily convened meetings long before any formal paper describing it had even been written. It would be several more months before the full results were checked, cross-referenced against one another, and finally published together, in the spring of the following year, as a cluster of 7 separate scientific papers, one from each instrument team, each one describing a different piece of the very same discovery from a different angle. 7 independent paths that all arrived at the same place. A small, unremarkable moon that had sat quietly in Saturn's shadow for more than 2 centuries, known for little more than shining a bit too brightly for its size, had just done something that upended a basic, long-settled assumption about how small icy worlds are supposed to age and, in time, fall still. Something underneath that ice was still generating heat, actively, in the present day, rather than merely coasting on some faint, leftover warmth from its violent birth billions of years before. And something underneath that ice was pushing material upward, through solid rock and solid ice, out through 4 narrow fractures at the pole, and off the moon entirely, fast enough and steadily enough that a spacecraft moving at many thousands of miles an hour could fly straight through the plume, gather its measurements, and still clearly recognize exactly what it had flown through. Cassini's mission planners took notice immediately. Flybys that had originally been designed for other purposes were reworked in the months and years that followed, sending the spacecraft back toward Enceladus's south pole again and again, far more often than the original mission plan had ever called for. An entire moon that had been a footnote suddenly promoted to one of the mission's central preoccupations, with dozens of dedicated encounters still ahead of it over the decade to come. Over the years that followed, as Cassini returned to Enceladus again and again, another pattern began to emerge, one that raised as many questions as it answered. The plume was not constant. Sometimes it sprayed more forcefully, sometimes less, and the pattern of that change seemed to track, roughly, with where Enceladus happened to be along its own orbit around Saturn at any given moment, as though something about the moon's shifting position relative to the planet's gravity was reaching down into the fractures themselves and controlling how widely they opened. Nobody could yet say precisely why. But it was one more piece of evidence that whatever was happening beneath those 4 cracks in the ice was not a fluke, not a one-time event caught by pure chance on a single lucky flyby. It was a system, an ongoing process, tied somehow to the mechanics of the moon's own orbit, still running, still active, more than a decade after that first July flyby, still waiting for someone to explain how a body this small managed to keep the whole thing going. What nobody could yet say, in the weeks and months following that July flyby, was where all of that material was actually coming from, or what, precisely, was supplying the energy needed to keep pushing it out so steadily, flyby after flyby, year after year. A plume, on its own, only tells you that something is escaping. It does not, by itself, tell you what lies beneath the fractures it is escaping from, whether it is venting from some shallow, isolated pocket of melted ice sitting close to the surface, the kind of thing that might freeze back over within a few thousand years and be gone, or from something far larger, far deeper, and far stranger, something that would take years of additional flybys, additional instruments, and an entirely different kind of measurement, one that had nothing to do with cameras or spectrographs at all, to finally pin down. Some on the mission team suspected, quietly, that they might be looking at something far bigger than a curiosity. Others were more cautious, unwilling to reach for the largest possible explanation before the smaller, simpler ones had been properly ruled out. Even the question of whether liquid water was involved at all remained genuinely open in those early months. Some researchers favored a simpler idea, that the fractures might be venting vapor directly from unusually warm ice, no liquid reservoir required, the solid ice slowly turning to gas, much the way dry ice does on a mild day here on Earth. Others suspected something far wetter, was at work somewhere beneath the surface, though nobody yet had a way to prove it, and both explanations fit the handful of measurements collected so far equally well. For now, in the summer of 2005, all anyone could say with any confidence was that the spray was real, that it showed no sign of stopping, and that it had to be coming from somewhere. The scientists who had spent that whole strange summer chasing the puzzle down knew better than to guess at an answer before the evidence could support one. All they had for now was a moon that refused to behave, a spray that refused to stop, and a question that would only grow more urgent the longer it went unanswered. Finding out exactly where the material was coming from would take the better part of the next decade, and it would begin with a question that had nothing to do with cameras at all. How much, exactly, does a plume like this weigh, and what could possibly be holding up the other end of it, far below the ice, out of sight of every instrument Cassini carried? That question, how much does a plume like this actually weigh, turned out to be exactly the right one to ask, and answering it meant turning to an instrument that had nothing to do with cameras or spectrographs at all. It meant weighing the moon itself. None of this happened quickly, and none of it happened by accident. Enceladus was hardly the first icy moon anyone had suspected of hiding water. Scientists had wondered about Jupiter's moon Europa in similar terms for decades already, ever since the Voyager and Galileo missions returned images of a surface crisscrossed with long cracks and ridges that looked, in places, disturbingly like pack ice on a frozen lake back on Earth. But wondering and confirming are two very different things, and Europa's own case had remained circumstantial for years, built on surface appearance and a handful of indirect measurements, rather than anything as direct as watching material actively erupt into space. Enceladus offered something Europa did not: a plume, spraying continuously, that could be flown through, sampled, and weighed. Whatever this small Saturnian moon turned out to be hiding, there was at least a real chance of finding out for certain, rather than simply arguing about it from a distance. Every object with mass pulls on every other object with mass, however faintly, and a spacecraft flying close enough to a moon will feel that pull as a tiny, measurable tug on its own path through space, speeding up almost imperceptibly as it approaches a concentration of extra mass and slowing down as it moves away from a deficit. On Earth, scientists had used a version of this same idea centuries earlier, back when 18th century surveyors noticed that a hanging plumb line, a simple weight on a string, would tilt just slightly off true vertical when suspended near a large mountain, tugged sideways by the mountain's own gravity. Cassini's radio signal worked on the same underlying principle, just measured with far greater precision, across a distance so great that a single radio message took well over an hour to complete the round trip between the spacecraft and the antennas listening for it on Earth. As the spacecraft passed close to Enceladus, giant dish antennas on Earth, part of a worldwide network of radio telescopes built specifically to keep in touch with spacecraft scattered across the solar system, listened for the faintest shift in the pitch of Cassini's radio transmission, a Doppler shift no larger than a few thousandths of an inch per second, smaller than the width of a human hair, measured over the course of a full second, which revealed exactly how the spacecraft's velocity was changing as it passed through the moon's gravity field. Map enough of those tiny velocity changes across enough flybys, and you can reconstruct where a moon's mass is concentrated and where it is not, the same way you might infer the shape of something hidden under a blanket just by running a hand carefully across the surface. By the time Cassini turned this technique on Enceladus, gravity mapping from orbit already had a proven track record elsewhere in the solar system, having been used before to probe the deep structure of the Moon, Mars, and other worlds. Nobody was inventing the method from scratch, for this particular moon. They were applying a well-tested tool to a genuinely new and unexpected target. Building a map precise enough to trust took several dedicated passes, spaced out across a handful of years, each one timed to bring the spacecraft over a slightly different part of the moon so that the completed picture would cover the whole gravitational field rather than just a single slice of it, patiently assembled one careful flyby at a time rather than settled in a single afternoon. There was no shortcut available. Every extra pass added one more thread to a picture that only became trustworthy once enough of those threads had been woven together. In 2014, a team led by scientist Luciano Es, an Italian researcher who had spent years refining exactly this kind of deep space gravity measurement across several different planetary missions, published the results of exactly that kind of mapping, built from several years of close Enceladus flybys. The gravity field around the moon's south pole did not match what a solid, uniform ball of ice and rock should produce. Something down there was less dense than solid ice, consistent with a body of liquid water sitting beneath the surface in that region, a finding that lined up neatly with everything the plume itself had already suggested. But the gravity data on its own left an important question unresolved. It could not fully distinguish between two very different possibilities: a large regional sea confined mostly to the area beneath the South Pole where all the activity was concentrated, or something that extended much further, wrapping the entire moon beneath its icy shell. Those two scenarios would have looked almost identical to a spacecraft measuring gravity from orbit, and yet they described two very different worlds. One was a moon with a warm, wet basement under one room of the house. The other was a moon that was, structurally speaking, almost entirely ocean, with only a thin shell of ice separating that ocean from space. Settling the question took a second technique entirely, one that had nothing to do with gravity and everything to do with watching the moon spin. Crack a hard-boiled egg and spin it on a table, and it rotates cleanly and predictably because the solid egg inside turns as one rigid piece along with its shell. Try the same thing with a raw egg, and the spin wobbles and hesitates in a way the boiled egg never does, because the liquid yolk and white inside are not rigidly attached to the shell. They lag behind, slosh, and drag against the shell's motion in ways that show up as an irregular, uneven spin. Enceladus does something remarkably similar over the course of each orbit around Saturn. Between 2004 and the years that followed, Cassini's cameras photographed the same surface landmarks, distinct craters and ridges scattered across the moon's icy face, over and over across dozens of separate flybys, building up an extraordinarily precise long-term record of exactly where those features sat relative to the moon's overall rotation at each pass. If Enceladus's icy shell were rigidly locked to a solid interior all the way down, those landmarks would return to almost exactly the same position, orbit after orbit, with only the tiniest and most predictable of variations easily calculated in advance. They did not. In 2016, a team led by scientist Peter Thomas published an analysis showing that Enceladus's shell rocks back and forth ever so slightly in a subtle wobble known as libration, and that the size of that wobble was too large to be explained by a shell locked to a solid body underneath. The wobble itself was tiny, far too small for any human eye to have noticed even standing on the moon's own surface, but large enough for Cassini's cameras, comparing the same landmarks across hundreds of images gathered over more than a decade, to measure with real confidence, patiently averaging away the noise until only the genuine signal remained. The only way to produce a wobble of that particular size was for the ice shell to be mechanically separated from the rocky interior by a layer of liquid water running underneath the entire moon, not just a pocket beneath one pole. The raw egg, not the hard-boiled one. Between the gravity measurements and the libration measurements, two entirely different techniques, built on two entirely different kinds of data, collected years apart by two different research teams working independently of one another. The case closed from both directions at once, each result standing on its own, and neither one depending on the other to be believed. Enceladus did not have a regional sea. It had a global ocean, wrapped entirely around a rocky core, hidden beneath an ice shell that, on average, ran somewhere in the range of 15 to 20 miles thick, thinning dramatically down to just a mile or two directly above the tiger stripes themselves, which helps explain why the venting happens exactly where it does and nowhere else on the moon. That thinning was not random, either. It matched, almost point for point, the same warm patch the infrared instrument had already mapped from a distance. Exactly the pattern you would expect if heat rising steadily from below were actively wearing the ice thin from underneath, rather than the shell simply happening to form unevenly by chance. The distinction was not just a technicality. A sea confined to one region could plausibly have been a temporary, localized pocket of melt, warmed by some passing burst of heat, and destined, eventually, to freeze solid again the way a puddle refreezes overnight. An ocean, wrapped around the entire rocky interior, was something else entirely. A structural, long-term feature of the moon itself, implying a heat source substantial and steady enough to keep the whole thing liquid, and a rocky core sitting in direct, continuous contact with liquid water across its entire surface, rather than at just one isolated patch. Once the global picture was confirmed, Cassini's remaining years at Saturn were reshaped around it almost entirely. Flybys that had once been considered a bonus, tacked onto a mission built primarily around Titan and Saturn's rings, were now treated as some of the most valuable encounters left on the calendar, each one an opportunity to fly a little closer, sample a little more directly, and press a little further into a question that had gone, in barely a decade, from an offhand curiosity to one of the central questions the entire mission still hoped to answer before it ran out of fuel. That still left the more basic problem sitting underneath all of it. Enceladus is small, distant, and by any conventional accounting should be cold clear through, keeping an entire global ocean liquid, rather than letting it freeze solid within a few 100 million years the way physics says a body this size ought to, requires a genuine source of ongoing heat, not just a one-time inheritance from the moon's formation billions of years ago. The answer turned out to lie in the shape of Enceladus's orbit itself. Left alone, gravity would eventually pull Enceladus into a perfectly circular path around Saturn, always at the same distance, feeling the same steady pull at every point along the way. But Enceladus is not left alone. Roughly twice for every one orbit that a more distant moon named Dione completes, Enceladus swings past it again, and that regularly repeating gravitational nudge, a relationship astronomers call an orbital resonance, keeps tugging Enceladus's orbit very slightly out of a perfect circle, and never lets it fully settle back down, the way a push timed just right can keep a swing moving indefinitely instead of gradually slowing to a stop. The timing is what makes it work, because the two moons fall back into the same relative alignment every single orbit. The nudge from Dione always lands at the same point in Enceladus's own path around Saturn, reinforcing the very same lopsidedness it created the time before, rather than arriving at random moments and slowly cancelling itself out. Because that orbit is not quite circular, Enceladus's distance from Saturn is constantly changing as it goes around, closer at some points, farther at others, and Saturn's gravity, being so much stronger up close than farther away, squeezes and stretches the little moon by a different amount at every point along its path. That repeated flexing works on Enceladus's interior, much the way bending a wire or a paperclip back and forth, over and over, will warm it in your fingers. The material does not break, but the constant, repeated deformation generates real, measurable heat, deep inside the moon, orbit after orbit, for as long as that lopsided orbital relationship with Dione keeps being renewed. That same flexing, it turned out, was also the answer to something left dangling earlier, a loose thread from the very start of this story. Why the plume's intensity rose and fell in step with where Enceladus happened to be along its own orbit. As the moon draws closer to Saturn and then swings farther away over each trip around, the changing squeeze on its icy shell opens and narrows the tiger stripes by tiny amounts, wide enough at some points in the orbit to let more spray escape, tighter at others to let less through. The fractures were not simply leaking at some constant, steady rate. They were breathing, opening and closing in rhythm with the same gravitational flexing that kept the ocean beneath them from freezing in the first place. One mechanism quietly explaining two mysteries at once. It is a strange kind of furnace, one stoked not by burning fuel or by radioactive decay, but by the simple, relentless mechanics of being squeezed unevenly, over and over, by a planet more than 700 times more massive than the moon it is squeezing. Tidal flexing alone, though, may not be enough on its own to explain everything the ocean would later reveal about itself. Producing water hot enough to leach minerals directly out of rock, as later evidence would show was happening, requires a genuinely vigorous heat source, and some researchers studying Enceladus's interior have suggested that flexing by itself might struggle to generate quite that much heat, at least not everywhere, all the time. A second process may be helping carry the load, a chemical reaction called serpentinization, which happens naturally whenever ocean water seeps into certain iron and magnesium-rich rock of exactly the kind a young, rocky core like Enceladus's would be expected to contain. That reaction releases heat as a straightforward byproduct of the chemistry itself, in something like the way a chemical hand warmer releases heat the moment its contents are allowed to react, no flame or fuel required, just a reaction proceeding on its own, once conditions allow it. If Enceladus's rocky interior is porous and fractured, rather than solid, the way some models now suggest, ocean water could be continuously seeping down into those cracks, reacting with the rock, warming, and rising back up again in an endless, self-sustaining cycle, tidal flexing and chemical reaction working together, rather than either one carrying the whole burden alone. With a genuine heat source identified and a global ocean confirmed by two independent methods, the next question was simply what that ocean actually was, chemically speaking, and the plume itself, once again, turned out to be the easiest way to find out. Each tiny ice grain launched from the tiger stripes is, in effect, a flash-frozen droplet of ocean water, captured at the instant it left the vents and preserved, more or less intact, for however long it takes a Cassini flyby to catch it and for an instrument called the Cosmic Dust Analyzer to record what it found. The eruption itself does much of that preservation work automatically. As ocean water is forced upward through the narrow fractures and out into the near-perfect vacuum of space, the sudden, drastic drop in pressure causes part of it to freeze into ice grains almost instantly, faster than any freezer on Earth could manage, while another portion boils directly away into vapor, without ever really passing through a liquid stage at all. The same basic physics that lets water boil at a noticeably lower temperature atop a tall mountain, where the air itself presses down with far less force. That near-instant freezing works in scientists' favor. It locks whatever the water happened to be carrying into a solid, largely unaltered state within a fraction of a second, preserving something close to a chemical snapshot of the ocean as it existed moments earlier, rather than letting it evaporate away, decompose, or react further once exposed to the open vacuum of space. That instrument works by letting individual grains, some no larger than a speck of household dust, strike a metal target plate at speeds of several miles per second, fast enough that the impact itself instantly vaporizes the grain and strips its atoms of their electrons. The resulting brief burst of charged particles is then sorted by mass. In much the same basic way, a prism sorts light by color, producing a kind of chemical fingerprint for every single grain the instrument manages to catch, one impact and one fingerprint at a time. Over the full span of the mission, that patient, one grain at a time process added up to hundreds of thousands of individual measurements, an enormous, slowly assembled catalog, built not from one dramatic reading, but from the sheer accumulated weight of paying close attention, flyby after flyby, for years on end. Not every grain told the same story. As scientist Frank Postberg and his colleagues first reported back in 2011 from an early pass through the plume's outer reaches, some grains were rich in dissolved salt, apparently flash frozen straight out of liquid ocean water during the brief, violent moment of eruption, while others carried almost no salt at all, closer in composition to plain water vapor that had condensed into ice only after it was already well clear of the vent. That difference mattered because the salt-rich grains, in particular, offered the clearest possible window into the ocean's actual chemistry, uncontaminated by whatever happened to the material on its way out. Sort the plume's output into these categories carefully enough, in other words, and the ocean itself begins to speak in its own voice, distinct from the noise of vapor and stray ice picked up along the way. It was an early and important clue, years before the gravity and libration studies confirmed the ocean's shape, that liquid water and not merely melting ice was involved in the first place, a hint of what the later, more rigorous techniques would go on to prove beyond reasonable doubt. Postberg's name would return to this story again and again as the plume kept yielding new secrets in the years that followed. Across thousands of these vaporized grains, a consistent chemical picture emerged from that salt-rich population. The ocean carries dissolved sodium and potassium, the same elements that give ordinary table salt and many mineral waters their character, along with chlorine and a family of carbonate and bicarbonate compounds. The same kind of chemistry you would find if you stirred a pinch of ordinary baking soda into a glass of water. Taken together, that mixture points to an ocean that is mildly salty and distinctly alkaline rather than acidic, closer in overall character to a glass of seltzer water with a little baking soda dissolved into it than to the acidic, corrosive chemistry many people might picture when they imagine an alien ocean. It is, in a strange way, a remarkably drinkable-sounding chemistry to find sealed beneath miles of ice on a moon this far from the sun, even if no one is suggesting anyone actually try. Researchers studying this composition began referring to it, informally, as a soda ocean, and the description has stuck for exactly that reason. It evokes something oddly familiar, chemically speaking, sitting inside one of the most remote and hostile environments in the solar system. Salt and alkalinity told scientists a great deal about the ocean's general character, But one particular category of particle, discovered within that same flood of cosmic dust analyzer data, told them something far more specific. Not just what the water was like, but how hot it had been at the exact moment certain minerals inside it had formed. These were tiny grains of silica, the same basic mineral that makes up ordinary quartz, and they were extraordinarily small, only a few nanometers across, smaller than most viruses, smaller than almost anything else that shows up anywhere in planetary science. What made them so revealing was not simply that they existed, but how narrowly consistent their size was from grain to grain. Nearly all of them clustered within the same few nanometer range, rather than spread across a broad mix of larger and smaller particles. That narrowness itself carried a message. If these grains had formed the ordinary way most fine dust forms, worn down gradually from larger rock fragments through years of grinding and impact, their sizes would come out scattered and uneven, a little of everything. A tight, narrow cluster, like the one Cassini actually measured, pointed instead toward the opposite kind of process, one where the particles came together all at once, in one sudden event, rather than being ground down slowly over time. On Earth, silica dissolves readily into water that is hot and alkaline, particularly water that has been in prolonged contact with certain kinds of rock deep underground. The same basic chemistry responsible for the mineral terraces built up over centuries at hot springs like the ones at Yellowstone, where scalding mineral-saturated water rises from underground, reaches the surface, and cools rapidly, forcing dissolved silica out of solution and depositing it as solid mineral almost immediately. The faster and more dramatic that temperature drop, the smaller and more uniform the resulting particles tend to be, because the silica has no time to slowly gather into larger crystals. It is forced out of solution all at once, nearly everywhere, in a narrow burst of nearly identical tiny grains. A team led by scientist Shang Wen-shu recognized this exact signature in the Enceladus data and ran a series of laboratory experiments to pin the numbers down precisely. Months of careful trial and error, mixing water at different temperatures and different levels of alkalinity, and checking which combinations produced silica grains matching the narrow size range Cassini had actually measured. Only water that had been in contact with rock at temperatures of at least 194 degrees Fahrenheit and at a moderately alkaline pH somewhere between 8.5 and 10.5 produced grains that small and that consistent. Cooler water, or water at a different acidity, either failed to produce silica grains of the right size at all, or produced a far wider, messier range of sizes than what the spacecraft had actually detected. It was a strange thing to hold in mind at once. A moon whose visible surface sits at temperatures that would be lethal in an instant, and whose ocean floor, hidden beneath miles of that same ice, was now shown to be running hot enough, in at least some places, to boil water on a stovetop back home. The silica grains were not the only category the cosmic dust analyzer had sorted out of the plume either. Alongside the salt-rich, ocean-sourced grains and the nearly pure salt-free ice, researchers had identified a third type entirely: grains carrying traces of organic material woven in among the ice itself, a category that would turn out to matter a great deal once instruments built specifically to analyze chemistry rather than just measure grain size got their own close look at the plume. That narrow window mattered enormously because it meant the grains themselves were carrying physical evidence of their own formation, baked directly into their size the way growth rings are baked into a tree trunk. This was not an indirect inference stacked on top of other assumptions. It was a thermometer of sorts, that had traveled from the ocean floor of another world, through miles of ice, out through a fracture at the South Pole, and into the collecting plate of a spacecraft passing by at many thousands of miles an hour, still carrying, in its size alone, a record of the exact conditions under which it had formed. And those conditions, water hot enough and alkaline enough to leach silica directly out of rock, are precisely the conditions found at hydrothermal vents on Earth's own ocean floor, places where mineral-rich water flows up through fractures in the sea floor and interacts directly with rock below. One question the grains could not settle on their own was how long any of this had actually been going on. A single snapshot of hot, alkaline water in contact with rock does not, by itself, say whether that contact began recently or has been running quietly for a large fraction of the Moon's entire 4.5 billion year history. Settling that question would take a different kind of evidence altogether, evidence that would only come later, once instruments built for chemistry rather than gravity or grain size had their own chance at the plume. Those vents themselves were only discovered on Earth in 1977, when a submersible exploring the seafloor near the Galapagos Islands stumbled onto towering mineral chimneys surrounded by an entire ecosystem thriving in complete darkness, a discovery that upended, at the time, the assumption that every food chain on the planet had to begin with sunlight. Their existence on Enceladus meant one more thing had to be true, something the gravity data and the libration data alone could never have shown. This ocean was not simply sitting passively inside a shell of ice, sealed off and unchanging. Somewhere far beneath the surface, water was actively moving through rock, hot enough to alter minerals and carry them upward, in a process still running today, driven by the same tidal flexing and very possibly the same chemical reaction, keeping the whole ocean from freezing in the first place. Enceladus was no longer alone in this picture either. In the years since, similar gravity and libration techniques, along with other lines of evidence, have pointed toward likely oceans hidden beneath the ice of several other distant moons, Europa among them, along with Jupiter's Ganymede and Callisto, and even hints of one inside the much smaller dwarf planet Ceres out in the asteroid belt. Hidden oceans, it turns out, may be a far more common feature of the outer solar system than anyone assumed, back when Voyager 2 first drifted past this part of space, decades before any of these techniques existed to look for them properly. But of that entire growing family, Enceladus remained the one case where a moon was actively, continuously handing samples of its own ocean directly to a passing spacecraft, without anyone needing to drill, land, or guess. Taken together, the picture that had come into focus was already remarkable enough on its own. A moon smaller than many American states holds, beneath an ice shell some 15 to 20 miles thick, a global ocean of liquid water kept from freezing by the relentless, repeated flexing of a lopsided orbit, salty and alkaline in character, and in direct, ongoing contact with a rocky seafloor, hot enough to drive real hydrothermal chemistry. Every piece of that description would have sounded, to a scientist working a generation earlier, like something borrowed from Earth's own deep sea, rather than a small, distant moon of Saturn. But a stage, however remarkable, is not the same thing as a story. Knowing that Enceladus has warm water in contact with rock says nothing yet about what that contact has actually produced, what molecules might have formed as water and mineral interacted over what may be billions of years, or whether any of it amounts to more than an elaborate, lifeless chemistry set. The ocean had been found, its shape confirmed twice over, its heat source identified, its general chemistry sketched out in broad strokes of salt and alkalinity. What was dissolved inside it, down to the individual molecules, and what those molecules might be capable of on their own, was still an entirely open question, one that gravity fields and libration measurements and even the silica grains themselves could not answer. That would take a different kind of instrument entirely, one built not to weigh the moon or watch it wobble, but to catch the plume's vapor directly and sort through its molecules one at a time. Every technique used so far, the gravity mapping, the wobble measurement, the grain size thermometry, had worked by inference, careful and rigorous inference, but inference all the same, reading the shape and structure of something never directly touched. What came next would be a more intimate kind of listening, sorting through the actual vapor and dust for the specific molecules riding inside it, and asking, for the first time, not just what the ocean was shaped like or how warm it ran, but what, precisely, it was made of, and what those particular ingredients, mixed together in a hot, salty, alkaline sea for who knows how long, might actually be capable of doing on their own. What those ingredients might actually be capable of doing on their own is a question that required a fundamentally different kind of instrument than anything used so far. Gravity data can weigh a moon. Grain size measurements can act as a thermometer, but neither one can tell you what molecules are actually riding along inside the spray. For that, Cassini needed to fly directly through the plume itself and let its vapor and gas pour straight into an instrument built to sort matter, not by size or mass distribution, but by identity, molecule by molecule. Everything discussed so far, the ocean's shape, its heat, its general character, had been inferred at arm's length, reconstructed from gravity fields and grain sizes the way a detective might reconstruct a room from footprints and fingerprints alone. What came next was closer to walking directly into that room and reading the labels on every bottle lined up along the shelf, still without ever being able to open one and taste what was inside. That instrument was Cassini's ion and neutral mass spectrometer, a device originally built to study the thin haze surrounding Saturn's largest moon, Titan, repurposed and pointed at a target nobody had designed it for. When the spacecraft first launched back in 1997, years before anyone suspected Enceladus had anything worth sampling at all, nothing about the instrument itself had to change to make this possible. It had always been built to sort gas by molecule, regardless of which moon that gas happened to be coming from, and Enceladus's unexpected plume simply gave it a second, entirely unplanned target to point at. Where the cosmic dust analyzer caught solid grains and vaporized them on impact, this instrument worked directly on the vapor and gas already present in the plume, drawing tiny amounts of it into a detection chamber through a narrow inlet and sorting the molecules inside by their mass, in effect, keeping a running count of exactly which kinds of molecules were present and in roughly what proportion, one fly-through at a time. The two instruments were, in a sense, reading two different halves of the same spray, one cataloging everything solid enough to strike a detector plate, the other cataloging everything still light enough to remain a gas. Flying an instrument like that through an active plume is a delicate maneuver in its own right. Cassini had to orient itself precisely, timing its approach so the inlet faced directly into the oncoming spray, catching material moving fast enough, and in some cases cold enough, that a poorly angled pass could have returned nothing usable at all. The molecules being searched for, hydrogen especially, were present only in small proportions relative to the water vapor that dominates the plume, meaning the instrument had to be sensitive enough to pick out a comparatively faint signal from within a much larger, much simpler background, the equivalent of trying to identify a handful of specific voices inside a crowded room from a recording made in a single, brief pass through the doorway. In 2017, a team led by scientist Hunter Waite published results from years of these direct fly-through measurements, and among the molecules identified was one whose presence carried an outsized significance far beyond its simplicity: molecular hydrogen, the lightest and simplest molecule that exists, made of nothing more than two hydrogen atoms bound together. On its own, hydrogen might seem like an unremarkable thing to find drifting through space, but on Earth's own seafloor, at hydrothermal vents very much like the ones this same investigation had already inferred beneath Enceladus's ice, hydrogen plays a specific and vital role. Certain single-celled organisms, called methanogens, survive by combining hydrogen with dissolved carbon dioxide, producing methane as a waste product, and, in the process, releasing usable chemical energy. In much the same basic way, a battery generates a current the instant its two internal chemicals are allowed to react with one another, harvesting the energy released as the reaction settles into a more stable arrangement. No sunlight is involved anywhere in that process. It happens in complete darkness, thousands of feet beneath the ocean surface, powered entirely by chemistry rather than photosynthesis, and it supports entire ecosystems on Earth's seafloor, communities of tube worms, crabs, and countless microorganisms clustered directly around vent openings that have never once depended on the sun for anything. Ecosystems of exactly the kind first stumbled upon near the Galapagos Islands and studied at length in the decades since at similar vent fields scattered across the world's ocean floors. Finding hydrogen streaming out of Enceladus's vents did not prove that anything similar was happening inside its ocean, but it meant, for the first time, that the specific chemical fuel such organisms would need was demonstrably present, not hypothetically possible but actually measured, drifting through space and directly into a spacecraft's own detector. The ocean had stopped being merely warm and salty. It now contained, in Cassini's own data, one of the precise ingredients life on Earth's seafloor runs on. That is, admittedly, a very particular kind of proof, and it is worth being precise about exactly what it does and does not establish. It shows that a necessary ingredient exists in the right place, at the right concentration, under the right conditions, not that anything has actually gone on to use it. A kitchen stocked with flour, sugar, and butter is not the same thing as a finished cake sitting warm on the counter, and every finding that followed this one would carry the exact same shape. Proof of ingredients, never proof of the thing those ingredients might, or might not, have become. 6 years later, in the summer of 2023, the plume delivered a second finding that closed one of the last remaining gaps in a very specific and very old scientific checklist. The pace itself was worth noticing. 11 years had separated the first blurry hint of a plume back in 2005 from confirmation of a global ocean in 2016. Barely more than half that many years now separated one landmark chemical finding from the next, as though the same, by then decades-old dataset, revisited again and again with sharper questions and better tools, kept finding new things to say. For decades, biologists and chemists studying the requirements for life as we understand it have organized their thinking around 6 elements, remembered by the shorthand CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Every one of them shows up somewhere essential in the chemistry of every living thing on Earth, woven into the basic machinery every cell depends on to function at all. Carbon forms the basic skeleton nearly every biological molecule is built around. Hydrogen and oxygen, together, make up the water every known form of life depends on, and appear throughout countless other biological molecules besides. Nitrogen is woven through every protein, and phosphorus holds together the genetic instructions inside every cell on the planet. By the early 2020s, Enceladus's ocean had already confirmed carbon, hydrogen, nitrogen, and oxygen folded into the salts, the silica, and now the hydrogen already measured. Phosphorus was the missing piece, and it was, in some ways, the hardest one to expect, since phosphorus tends to lock itself tightly into certain minerals and dissolves into ordinary seawater only reluctantly, even on Earth. Frank Postberg, the same scientist whose earlier work had first distinguished salt-rich ice grains from salt-poor ones, spent years searching specifically for phosphorus in the plume data without success before his team finally tracked it down, publishing the finding in June of 2023. The search itself illustrates something about how this entire investigation has actually proceeded, a pattern worth noticing precisely because it runs counter to how discoveries like this are often imagined. It was not a single triumphant scan turning up an unmistakable signal on the first attempt. It was a specific researcher already deeply familiar with this exact dataset, returning to it again and again over the better part of a decade, refining the search each time, tightening the analysis a little further with each new pass, until the evidence finally became clear enough to publish with confidence. Buried within a subset of salt-rich grains, the kind already established as flash-frozen samples of actual ocean water, the cosmic dust analyzer had picked up phosphate, a phosphorus-bearing compound, and not in trace amounts. The concentration measured was at least 100 times higher than phosphate levels found in Earth's own oceans, an almost startling degree of enrichment for an element that, under most ordinary conditions, resists dissolving into seawater at all. The likely explanation traced directly back to the ocean's chemistry established earlier, an alkaline, carbonate-rich soda ocean of exactly the kind Enceladus's plume had already revealed, is unusually effective at pulling phosphorus-bearing minerals out of rock and keeping that phosphorus dissolved rather than letting it settle back out. The same basic chemistry, in miniature, behind why certain alkaline lakes here on Earth, the Great Salt Lake among them, can carry mineral concentrations wildly out of proportion to the ocean water most people picture when they imagine a sea. It was a satisfying piece of the puzzle to have fall into place. The very ocean chemistry inferred years earlier from nothing more than a handful of salt and carbonate readings had just turned out to also explain why an element as reluctant as phosphorus would show up at all. One already established finding quietly making sense of a brand new one. Phosphorus matters enormously to biology specifically because it forms the structural backbone of DNA and RNA, the molecules every living thing on Earth uses to store and copy genetic information. Picture the familiar twisting ladder shape of a DNA strand, and phosphorus is quite literally load-bearing within it, forming, together with a simple sugar, the two long rails the ladder's rungs are strung between, holding the whole structure together the way rungs hold together the sides of a ladder. And it is also the key working part of adenosine triphosphate, the molecule every cell on this planet burns, quite literally, as its basic unit of usable energy, thousands of times over, inside a single cell, every minute, recharged and spent again and again the way a rechargeable battery cycles through use and renewal, except doing so at a scale and speed that never really stops for as long as the cell itself remains alive. With phosphorus confirmed, 5 of the 6 CH-NOPS elements had now been directly measured inside Enceladus's ocean. Sulfur remains the holdout. A faint signal, consistent with hydrogen sulfide, has turned up in some of the data, but it cannot yet be cleanly separated from other molecules of a similar mass riding along at nearly the same weight, and until it can, sulfur stays officially unconfirmed rather than merely overlooked. Closing that particular gap will likely take a more sensitive instrument than anything Cassini carried, purpose-built to tease apart molecules that current data simply cannot distinguish from one another. One more item on a growing list of questions. No amount of additional analysis of Cassini's existing archive will ever be able to answer on its own. Enceladus has not completed the checklist. It has completed 5/6 of it, a distinction worth holding onto rather than rounding up for the sake of a tidier story. The very same December 2023 season brought a third and complementary finding, this time from a team led by scientist Jonah Peter, who identified an entire family of additional molecules riding in the plume's vapor: hydrogen cyanide, acetylene, propylene, and ethane. The first of those names tends to catch people off guard, since cyanide carries an unmistakably grim reputation on Earth, tied almost exclusively in the public imagination to poison. Among chemists studying the origins of life, though hydrogen cyanide holds a very different reputation entirely. It is considered one of the single most useful building block molecules available in prebiotic chemistry, capable of reacting further under the right conditions to help form amino acids, the components proteins are built from, and the nuclear bases that make up the genetic code itself. Laboratory experiments going back decades, mixing simple starting molecules under conditions meant to mimic an early planet, have repeatedly turned to hydrogen cyanide as one of the most productive ingredients available for building the kind of complex organic chemistry life eventually depends on, sometimes producing from nothing more than hydrogen cyanide and a handful of other simple molecules left to react over time. The same basic amino acids found in proteins throughout the natural world. Its presence in Enceladus's plume does not mean anything sinister is happening inside the ocean, whatever the word's grim reputation on Earth might suggest to a first-time listener. It means one of the most versatile starting materials chemists know of, the kind laboratory experiments have used for decades to explore how life's basic molecules might first assemble themselves, is already there, waiting, dissolved in a sea already shown to be warm, alkaline, and rich in phosphorus. One more entry on a list that kept growing longer and harder to explain away with each passing year. Acetylene, propylene, and ethane belong to a simpler, more familiar chemical family. Light hydrocarbons, close relatives of the propane that fuels a backyard grill or an outdoor heater, built from nothing more than carbon and hydrogen strung together, in short, simple chains. Ethane, in particular, is a near cousin of natural gas itself, the same basic category of molecule burned in furnaces and stovetops across the country every single day. Propylene, closely related to the propane in that same backyard tank, and acetylene, a gas familiar to anyone who has ever watched a welder's torch throw off its bright blue-white flame, round out the family, each one a slightly different arrangement of the same basic carbon and hydrogen building blocks. On Earth, certain microorganisms are able to use molecules exactly like these as an energy source, breaking their chemical bonds apart to release usable energy in much the same basic sense that methanogens use hydrogen, just through a different chemical pathway. None of these three, whatever their unfamiliar scientific names might suggest to a first-time listener, are exotic in the way they might sound. They are, chemically speaking, close relatives of some of the simplest and most common fuels used on Earth every day. Individually, none of these four molecules proves anything about life. Together, they describe an ocean carrying not just the raw elements biology depends on, but several of the specific, ready-to-use compounds living systems on Earth are already known to run on. Sitting in the same warm, salty, phosphorus-rich water Cassini had already sampled from a dozen different angles. It is the accumulation that carries the weight here, not any single entry taken alone off the list. A single interesting molecule, found once, could plausibly be dismissed as a fluke of chemistry, a one-off compound with no larger story attached, easy enough to set aside and forget without much consequence. An entire, mutually consistent set, energy sources, structural elements, and the specific building blocks known to assemble into more complex molecules, all found together in the same body of water, drawn from the same ocean by the same handful of fractures, is a great deal harder to wave away as coincidence. By the time both of those 2023 findings were published, an entirely different instrument, one that had never flown anywhere near Saturn at all, was about to reveal something about the plume that no fly-through measurement, however close, could ever have shown on its own. Just how large the whole system actually was. The James Webb Space Telescope, orbiting nearly 1 million miles from Earth in the opposite direction from Saturn, does not fly through anything. It watches from a great distance, using an instrument called a near-infrared spectrograph to read the faint chemical fingerprint left behind as sunlight passes through the plume's vapor, spreading that light out the way a prism spreads sunlight into a rainbow, and looking for the exact, narrow bands where water vapor absorbs a portion of it, a signature no other kind of material would produce in quite the same pattern. Every molecule absorbs and releases light at its own particular set of wavelengths, as distinctive, in its own way, as a fingerprint, and reading those wavelengths carefully enough lets an instrument identify exactly what it is looking at, without ever needing to touch the material directly, an approach that works just as well studying a plume around a small moon of Saturn as it does studying the atmosphere of a planet orbiting a distant star hundreds of light years away. The very same telescope built to study the earliest galaxies pressed into service for a handful of hours on a target considerably closer to home. It is a technique built entirely around patience and distance rather than proximity, the opposite approach in almost every respect, from flying a spacecraft directly through a plume and letting matter strike a detector plate. In 2023, a team led by scientist Geronimo Villanueva pointed that instrument at Enceladus and measured the plume extending far beyond anything Cassini's own cameras, built for close-range imaging rather than wide-field views from afar, had ever been able to frame in a single photograph, reaching up to roughly 10,000 kilometers from the Moon's south pole, a plume nearly as wide as the diameter of the entire planet Earth, erupting continuously from a moon whose own diameter would fit inside that plume nearly 20 times over. Material was leaving Enceladus at a rate of roughly 300 kilograms every second, close to the weight of a small car launched off the moon's surface every single second, without pause, for as long as anyone has been measuring it. A figure that matched what Cassini's older, closer-range instruments had already estimated decades earlier, now confirmed independently from a telescope, sitting nearly 1 million miles from Saturn in the opposite direction. Roughly 30% of that escaping water, the Webb data showed, settles into a faint, sprawling ring of vapor that circles the entirety of Saturn essentially a second, much larger, and far less visible companion to Saturn's famous, brilliant rings of ice. Built entirely from Enceladus's own exhaled breath, rather than from any ancient collision or captured debris. Saturn's icy rings themselves owe at least part of their brightness to this same steady supply, fresh material, continually replenishing the outermost, faintest of those rings from a single small moon tucked inside it. The remaining 70% escapes the Saturn system entirely, drifting outward into the wider solar system, carrying trace amounts of Enceladus's ocean chemistry with it, long after any spacecraft could hope to follow. That two very different kinds of measurement, one gathered by flying directly through the plume at close range, and one gathered by reading its faint chemical signature from a telescope parked nearly 1,000,000 miles from Saturn, arrived at matching numbers. For how much material Enceladus was losing mattered a great deal on its own. Independent confirmation, arrived at through two completely unrelated methods, is exactly the kind of agreement that turns a single measurement into something scientists can actually build further conclusions on top of. It is also a genuine luxury unavailable almost anywhere else in the search for ocean worlds. A telescope sitting near Earth can only read a plume's chemistry if that plume actually exists and reaches far enough into space to be seen from so great a distance. Most suspected ocean worlds offer nothing of the kind, their hidden water sealed away behind miles of unbroken ice with no vent, no plume, and no way for a telescope or a passing spacecraft to sample so much as a single molecule without landing and drilling down directly, an undertaking no mission has yet attempted anywhere in the outer solar system. Enceladus remains the rare exception that simply hands its water away freely and continuously to anyone patient enough and well-equipped enough to be in a position to catch it. That image, a moon smaller than many American states quietly supplying an entire ring system's worth of material to the planet it orbits, its own gravity too weak to hold on to more than a fraction of what it vents, made an old assumption harder and harder to hold on to. The idea that whatever chemistry was happening inside Enceladus's ocean might be some ancient, one-time event, a chemical accident that occurred early in the moon's history and simply happened to get frozen into the ice before anyone arrived to look. A plume spraying material at a measured, ongoing 300 kilogram per second rate, feeding a torus that stretches around an entire planet, is not the signature of something that already finished happening. It is the signature of something still running in the present tense, exactly as Cassini's earliest images had first suggested nearly 2 decades earlier. The most recent piece of this particular puzzle came not from a new spacecraft or a new telescope, but from a fresh look at material Cassini had already collected years before it stopped flying. Most of the ice grains analyzed over the mission's lifetime had spent a long time drifting through Saturn's E-ring before any instrument caught them, exposed the whole while to a harsh bath of radiation from Saturn's own magnetic environment, the same kind of exposure that, on Earth, will slowly bleach color from a flag left flying too long in direct sun, breaking complex molecules down into simpler fragments the longer they sit exposed to it. But one particular flyby, designated E5 in the mission's own records and flown years before this fresher analysis was ever conducted, brought Cassini through the plume close and fast enough, moving at roughly 11 miles per second relative to the moon, that the spacecraft passed directly through freshly ejected material only minutes removed from the vents themselves, offered something rarer, a sample that radiation had barely had time to touch. The data from that flyby had been sitting in the mission's archives for years already, waiting for exactly the kind of careful reanalysis that finally arrived in 2012. 2025. In 2025, a team led by scientist Nozer Kawaja finished analyzing data from that flyby and found something the older, radiation-aged E-ring grains had never shown. Entirely new classes of organic fragments, including esters and alkenes, both families of carbon-based molecules built around specific, fragile chemical bonds that radiation tends to break apart fairly quickly once exposed, along with ethers and aromatic compounds. Ringed molecular structures chemists recognize as some of the more elaborate, structurally complex organic building blocks identified in the plume to date, closer in sophistication to molecules found in certain carbon-rich meteorites than to the simpler hydrocarbons identified back in 2023. These were not new discoveries because the ocean had suddenly started producing new chemistry that summer. They were new discoveries because, for the first time, scientists were looking at a sample close enough to its source that radiation had not yet had the chance to erase what was originally there, chemistry that had likely been present in every plume since Cassini's first flyby, simply invisible until someone caught it early enough. It is a little like judging a dish only by its leftovers, reheated and left sitting out for days, and then finally getting a taste of it fresh off the stove. The ingredients were never actually different. Only the freshness of the sample was, and freshness, it turned out, changed what could actually be recognized on the plate. That distinction, fresh grains against aged ones, said something important all on its own, well beyond the specific molecules it revealed. A reminder that even within Cassini's own decade-plus of archived data, not every sample was created equal, and some had simply been waiting, quietly, for the right question to be asked of them. Even the most direct sample of Enceladus's ocean anyone has ever collected was still, by the time it reached a detector, minutes old, already flash-frozen, already exposed to the vacuum of space. Already, partway through, however much radiation exposure, it managed to accumulate on its short trip from vent to spacecraft. No sample gathered so far, no matter how fresh, has ever been the ocean itself, untouched and unaltered. Every single one has been the ocean's exhale, caught mid-breath, already changed in some small way by the simple, violent act of leaving. Consider everything that has to happen to a single molecule between the ocean floor and a spacecraft's detector. It has to survive being carried upward through miles of fractured ice, past whatever chemical changes that journey through rock and ice might introduce along the way, survive the violent pressure drop of shooting out into open vacuum, survive flash freezing or boiling away entirely, and then survive however many minutes or years of exposure to Saturn's radiation environment pass before an instrument happens to be in the right place to catch it. Any given molecule might not survive that journey chemically intact at all, and there is, at present, no reliable way to know for certain which ones made it through unchanged, and which ones were subtly altered somewhere along the way. That gap between what the plume reveals and what actually exists unaltered in the water far below the ice would turn out to matter more than almost anything else this investigation had uncovered. A limitation no amount of additional fly-through sampling, however sophisticated the instrument, could ever fully close on its own. Reading the spray, however carefully, however many different instruments are brought to bear on it, will only ever be reading the spray, taken together. The picture built across these findings was no longer just a description of interesting chemistry sitting inertly inside a hidden ocean. It was hydrogen, ready to fuel exactly the kind of energy-yielding reaction certain organisms on Earth's own seafloor depend on. It was phosphorus, the backbone of genetic material and cellular energy alike, present in concentrations far richer than Earth's own ocean carries. It was hydrogen cyanide and a family of simple hydrocarbons, precisely the sort of versatile building blocks and ready fuel sources laboratory chemistry has spent decades studying, in flasks and test tubes here on Earth, as candidates for how life's ingredients might first come together. And it was, according to the very latest look at the freshest material anyone has ever managed to catch, still actively producing new organic complexity today, not billions of years ago. None of these findings arrived at once, and none of them came from the same instrument, the same spacecraft, or even the same decade. A device built for Titan found the hydrogen. A dust detector built to study ice grains found the phosphorus. A different kind of vapor analysis, running alongside it, found the hydrogen cyanide and the simple hydrocarbons. A telescope that has never left Earth's own orbit found the plume's true size. And a second look at years-old archived data, revisited only because someone thought to ask whether a fresher sample might show something the first pass had missed, found the newest organic chemistry of all. 4 different tools, 4 different teams, 4 different moments scattered across nearly a decade, each one adding its own separate thread to the same accumulating rope, none of them alone strong enough on its own to hold much weight. All of them woven together considerably harder to dismiss. This no longer read like a chemical accident, preserved by cold and frozen in time since the earliest days of the solar system, a fossil of chemistry that simply happened to survive intact. It read like an active, ongoing system, still running, still producing, still worth watching closely, right now, in the present tense, rather than as a relic of the distant past, which raised an obvious question, one that this string of chemical discoveries alone could never fully answer. Was any of this still happening right now, in the same way, and at the same intensity Cassini had measured years ago? Or had something about Enceladus already begun, slowly, to change since the spacecraft itself stopped watching? By then, Cassini itself was no longer available to check. In September of 2017, deliberately and by design, the mission ended with the spacecraft diving straight into Saturn's own atmosphere and burning apart. A final maneuver chosen specifically to eliminate any chance, however remote, that a lifeless, well-traveled spacecraft might someday drift into Enceladus itself and contaminate the very ocean it had spent 13 years learning to respect from a careful distance. That question, whether Enceladus was still doing today what Cassini had first caught it doing 2 decades earlier, did not stay open for long. The answer arrived in 2 separate pieces, gathered years after the spacecraft itself had gone silent, both pulled from data the mission had already brought home, and simply never finished asking every possible question of. Proof that a finished mission and a finished investigation are not always the same thing. The first piece concerned heat, and it required looking somewhere nobody had thought to look closely before: the North Pole. Every measurement of Enceladus's internal warmth up to this point had come from the south, where the tiger stripes vent their spray in plain view and where Cassini's infrared instrument had found gigawatts of heat pouring out from the very beginning. The North Pole, by comparison, had always looked like the moon's other unremarkable face, more heavily cratered, visibly older, showing none of the young, smooth terrain that marks the south as a place still being reshaped from below. In photographs, it looked, if anything, like one of Enceladus's own quiet, geologically finished neighbors, closer in appearance to Mimas or Tethys than to the restless landscape surrounding the tiger stripes on the opposite side of the same small moon. For years, the working assumption was simple. Whatever engine was heating Enceladus, It was a South Pole phenomenon, tied specifically to the fractures already mapped in detail. A team of researchers from Oxford University, the Southwest Research Institute, and the Planetary Science Institute in Arizona, working together across 3 separate institutions and, in some cases, 3 separate continents, decided to test that assumption directly, comparing infrared readings of the North Pole taken by Cassini's composite infrared spectrometer during 2 very different moments in the Moon's long year. One taken during the depths of northern winter, not long after Cassini first arrived at Saturn, and another taken a full season later, during northern summer, roughly a decade afterward. Enceladus circles Saturn itself in about a day, but for the purposes of seasons, what matters is Saturn's own much longer path around the Sun, nearly 30 years to complete just one circuit, a journey Enceladus rides along with as it orbits its much larger companion. Whichever concept eventually flies, if either one ever actually does, the basic task facing it remains the same: to do what no mission has yet done at Enceladus, and make actual contact with material that has not already been altered by miles of ice, a violent pressure drop, and however many years of drifting through Saturn's radiation environment before reaching a detector. It is worth remembering here just how much of this entire story was gathered by instruments never built for this purpose in the first place. A camera meant to photograph rings caught the plume. A magnetometer meant to study Saturn's own field caught the first hint of an atmosphere that should not have existed. A dust analyzer meant to catalog debris caught salt, then silica, then phosphorus. Each one a fresh surprise to an instrument that had never been told to expect any of it. A mass spectrometer built for Titan's haze caught hydrogen meant to fuel life it was never designed to look for. Cassini stumbled into nearly every one of its Enceladus discoveries sideways, using tools built for other jobs entirely, on a mission that had never once listed this small moon among its primary objectives. Orbelander and its European counterpart represent something this story has never actually had before: instruments built on purpose, from the very first sketch, for exactly this question. A lander sitting directly on the icy crust, drawing in freshly fallen plume material within moments of it settling back onto the surface, would close a meaningful part of that gap, catching material before it has traveled nearly as far or been exposed to nearly as much radiation as anything Cassini ever managed to sample from a passing flyby. Even that, though, would still fall short of the ocean itself, sealed away beneath ice that, by the most recent estimates, runs somewhere between roughly 12 and 18 miles thick across most of the Moon, considerably thicker everywhere outside the narrow band directly over the tiger stripes. Nobody currently on the table is proposing to drill or melt through that much ice, an engineering undertaking well beyond anything either concept currently envisions. The honest goal of every mission concept now under discussion is not to reach the ocean directly, but simply to get close enough and analyze carefully enough to finally ask the one question this entire 21-year chain of evidence has been circling from the very start, using instruments actually built for the job rather than repurposed after the fact from instruments designed to study something else entirely. Before turning to what still lies beyond reach, it is worth sitting with what that chain of evidence actually adds up to and what it does not, if only because a case built this patiently over this many years deserves a moment of genuine reflection before moving on to what remains unanswered. 21 years ago, Enceladus was, to nearly everyone paying attention, exactly what it appeared to be from Herschel's own telescope more than 2 centuries earlier: a small, distant, forgettable point of light, notable mainly for shining a little too brightly for its size, a footnote in a mission built around its far larger neighbors. Nobody built Cassini to look for life there. Nobody expected the moon to matter much at all, and nothing in the mission's original plans reserved anything more than a handful of passing glances for it. And yet, one careful measurement at a time across 4 different spacecraft instruments never designed to work together, across a telescope that has never left the vicinity of Earth, across teams of scientists scattered over 3 different continents and more than 2 decades, largely without any of them setting out, from the beginning, to build a case for anything in particular. That is precisely what has happened. Nobody sat down in 2005 watching those first faint jets appear in a backlit photograph and declared that Enceladus would become one of the 2 or 3 most promising places in the entire solar system to search for life beyond Earth. That conclusion built itself, slowly and almost accidentally, out of 2 decades of unrelated researchers, each answering their own narrow question, and then, almost as an afterthought, noticing how neatly their answer fit alongside everyone else's. One more stone, settling into place beside all the others. There is something worth pausing on in that, beyond the science itself. Most of what humanity thinks it knows about the universe arrives in a single dramatic report, a signal detected, an image captured, a discovery announced, a headline written the same week. Enceladus's case was never built that way, and in a sense, it never could have been. It was built the way a stone wall gets built without mortar, the kind still standing after centuries in old New England pastures and hillside farms. One carefully chosen stone set down at a time, by whoever happened to be clearing that field that particular season. Each one selected because it happens to rest solidly against the stones already in place. No single stone holding up the structure on its own, the whole arrangement gaining its strength only from how completely each new piece fits against everything laid before it. Nobody who set the first stone in a wall like that could have pictured exactly how the finished wall would eventually run across the whole hillside. Nobody who watched Cassini's magnetometer twitch strangely on a single flyby in February of 2005 could have pictured a moon confirmed 2 decades later to be venting phosphorus and hydrogen cyanide from a stable, hydrothermally active global ocean into a lattice of electromagnetic structure 500,000 kilometers wide. And yet here, that wall now stands, built by hands that never coordinated with one another, added to across 3 continents and more than 20 years, by teams who were each, in the moment, simply trying to answer one small, specific question of their own. A gravity measurement here, a libration study there, a grain of silica smaller than a virus, carrying a temperature reading from an ocean floor no human being has ever seen, a telescope, built to study the light of galaxies billions of years old, turned for a handful of hours toward a plume erupting from a moon barely a few hundred miles across. A magnetometer twitch, dismissed at first as noise, that eventually grew into a 500,000 kilometer web of electromagnetic structure. None of those pieces, taken alone and set down on a table by itself, would justify much excitement at all. Stacked together, patiently, over 21 years, they have produced something that now genuinely resembles a case in the fullest sense of that word. Not a hunch, not a hope, but an argument, built piece by piece from independently gathered evidence, all of it still pointing the same quiet direction. What it has not produced, and what it cannot produce without a fundamentally different kind of mission, is an answer. Every finding recounted across this entire story, every gravity map, every wobble measurement, every grain of silica and molecule of hydrogen cyanide, describes a moon capable of supporting the kind of chemistry life on Earth depends on. Not one of them describes life itself. Capable of is a phrase this entire investigation has earned the right to use, repeatedly and honestly, across 21 years of careful, independently confirmed evidence. Does is a phrase it has not yet earned and cannot honestly claim, no matter how completely the surrounding case has been built. That gap between capable of and actually does is not a small technicality left over at the end of an otherwise finished investigation. It may be the single largest unanswered question left anywhere in the solar system, sitting exactly where 21 years of increasingly sophisticated evidence has patiently carried it, and no amount of additional analysis of Cassini's existing archive, however clever, however patient, will ever be capable of closing it. Closing it will take a spacecraft willing to go back, sit down, and actually touch what has, for 21 years now, only ever been read from a distance, catalogued, measured, and inferred, but never once directly held. For now, that is where the story rests. Somewhere out past the orbit of Mars, past the asteroid belt, farther still, out where sunlight has thinned to almost nothing, a small moon most people had never heard of 2 decades ago continues its quiet, unhurried circuit around a ringed planet, venting a plume of ice and vapor into space exactly as it has for as long as anyone has been watching, catching what little light reaches it and scattering that light back out into the dark exactly as it has since, long before Herschel ever pointed a telescope its way. It carries with it salts and phosphorus and hydrogen and a slowly growing catalogue of organic chemistry, and, somewhere beneath all of that ice, a warm, dark ocean that has now told humanity nearly everything it is capable of telling from a distance. Whether anything living has ever stirred in that darkness remains exactly what it was the day Cassini first caught sight of that impossible plume. A real, open, unresolved question, patiently waiting, along with the rest of that quiet ocean, for someone to finally come back and ask it properly. Sleep now and drift toward morning while a hidden sea breathes beneath the ice.